All right, hello everyone for our first post-lunch session in this room. Right now we're going to have a talk presented by Brett Slatkin, the author of Effective Python. The talk will be about the Zen of Polymorphism, choosing between isinstance, and I won't pronounce the brackets in English, methods, and single dispatch. Please give him a round of applause.
Can everybody hear me okay? Great. Yeah, it's great to be back at PyCon. It's been a while, so really good to be here in person. So I'm going to talk to you today about the Zen of Polymorphism. You might have heard of the Zen of Python, which is kind of a set of rules of, good rules of thumb for how to write Python code. And so I'm trying with this talk to give you the same kind of rules of thumb for polymorphism in general. So let's start with a scenario, and we're kind of going to talk through this with this scenario. So let's say you're building a calculator program, something that's going to take some kind of formulas and then parse them into some object tree as your first step, and then you're going to calculate the result by walking over that data structure and doing some computation. So sometimes it's called like a tree walking interpreter, but let's just call it a calculator program. So let's try to do that. Well, the first thing we would do is we'd declare some data types. So something to represent numbers, something for the add operation, which has a left and a right node. Then multiply is kind of very similar. And then we would parse. We'd have a parser. I'm not going to write a parser during this talk, don't worry. But let's just assume we have one. Okay, so that we have this parse formula function. It's going to take a string, and it's going to somehow magically turn that into a tree, which is this tree down here, this tree data structure. So there's a multiply object, and inside the multiply object is an add object on the left side over here. And then, let me get my mouse over here. And then on the right side is another add operation with 4 and 7. So you have this kind of tree-like structure that represents the string of that formula. So it's very, very straightforward. So now let's talk about 4 different ways you can actually calculate the result of this formula using polymorphism. And these are all kind of standard techniques that maybe you've heard of, maybe some of them you haven't. So we're going to compare and contrast a bunch of these and kind of see what are the strengths and weaknesses and how can they build on each other to make something better. So the first one is one big function. This is what you probably should do first. This is basically, most of my code looks like this, which means that it's super ugly, where you create a calculate function and you just look at the node you have and you say, hey, what kind of node is this? Is it an integer? Well, if it's an integer, then just grab the value attribute. If it's an addition, then I know I have to do some kind of recursive formula here, right? Go down to the left node and I calculate its value, and I go down to the other node and I calculate its value, and then add them together, and that's my operation. I'm going to show you this in more detail in just a second, so don't worry. Multiply, same thing. Calculate both of the nodes, multiply them together, and return the result. And if you don't know what the node type is, you haven't seen it before, you just return an error. You're like, I don't know what that is. So this works just fine, works great, uses isinstance, which is basically like, is this object a type of this class? That's what it does. It's built in. Just to be really clear, so let's do calculate on this tree that we just had. So it's going to, for the blue node, it's going to call calculate. The blue node is a multiply node. So then that's going to first calculate the left side, which is an add node, the purple one. That purple one is going to take the 2 sides and add them together to create 8. 3 plus 5 is 8, and return 8. Then the multiply node is going to go down the right side. For the addition, it's going to grab the left node 4 and 7. It's going to add them together, make 11, and then it's going to, the multiply node, the blue node again, is going to multiply them together. 8 times 11 is 88. Okay, so everybody follow this? We get the tree logic. Are we good so far? Okay. So now let's make this more complicated. Let's add a new operation, because calculators have all kinds of operations. We didn't even have subtract yet, so we need like a lot more than that in order to make this a useful program. So let's add a power where you take some base, 2 to the 3rd power, that kind of thing. So the data part of this is pretty easy. We create a new class to contain the data, includes the base and the exponent. Okay, pretty easy. But then the calculate function, we have to add another entry to it, this power function. We need to have another isinstance check. And that isinstance check needs to do the actual operation to apply the calculation. And so for like a couple of different objects and operation types, this is fine. But the issue is, over time, this is just going to get longer and longer and longer. And then it's fairly sensitive to ordering, because if let's say you have an integer class and you have a positive integer class or something like that, they're superclasses of each other, and now the order really matters in which order you check the instances, or else you're gonna get some weird behavior. So this ends up being really brittle. But anyway, we added it here. We added the power object class, and now we can use it. We can create a new formula, like 2 to the third plus 4. We parse that into this tree, and then when we run the tree here, what we see it doing when it's calculating this new value off this new tree, it's calling the logic for the power operation. So it knows, hey, I got to calculate the base and I got to calculate the exponent, and now I can do all these operations and get the right answer. So again, none of this should be surprising. This is pretty straightforward. Another thing you might want to do is you might want to say, hey, I have another type that I want to add in here that's totally different, maybe a subclass of an existing thing like positive integer I was talking about. In that case, I can just add it because it has the same behavior as before. So I just add that new class, and nothing has to change. It just magically works because the one big old function of calculate already knows how to deal with it. So that's a nice thing. Now let's do one other thing you want to do. I have this nice data class with this hierarchy of this formula. Let's say I want to pretty print it. I don't want to just calculate the values, but I want to print it back out again for debugging purposes or serialization or something like that. Well, now I have to create another big old function. And this new big old function looks a lot like the other big function, and it basically duplicates all of the isinstance class statements, and it also duplicates all of the node traversals like node.left and node.right and calling pretty and recursion. And so there's a ton of duplication in this every time you want to add some new thing that traverses the same data, which is really a lot of duplication and chance for new bugs. So the one big function approach has, it's nice that it's simple. The control flow is really simple. It's easy to debug because it's just one stack, but it's this huge thing that's monolithic. It gets super long. And then if you want to create new functions, you have to duplicate them. So this is why one big function is like probably not the right choice. In a small function, if it's just a few if statements, like clauses, that's fine. But once you get to like 4 or 5, 6, if you know you're going to get up to 20 or something like that, there's just no way this is going to work. It's going to be terrible. So then people are like, okay, well, that's why you do object-oriented programming, right? Okay, let's see if that's true. But people often say that object-oriented programming is a solution to this problem because it lets you avoid writing if statements. So let's make an OOP version of this. So again, we have these classes, the node class, integer class. So the node base class, which has a calculated, oh, did I lose it? Am I back? Oh, okay. So there's a node class with a calculate method that doesn't do anything by default. And then we specialize it for each of the classes. So for an integer, you just return the value. For addition, you calculate the left side and calculate the right side and then add them together. For multiply, you calculate the left and the right and then you multiply them together. So very very simple OOP program. And if you look at what it actually does, this is just supposed to be like a stack trace of the two ways. So on the left is what you already saw before of how we calculated 88 using just normal old functions. And I'm just trying to show you here that the right side with OOP is doing exactly the same thing. It's just the functions have different names. It's instead of it being calculate in one big old function, multiply.calculate knows that it calls add.calculate, which calls integer.calculate, and the runtime, Python's runtime just takes care of that for you. It's like based on the type of the object you're calling, it knows which function or method, specialized method to call. It calls it for you. You don't have to worry about it, and it's all taken care of, and standard and all that kind of stuff. So that's the kind of very nice benefit of object-oriented programming, and it seems like a really big win. And it's like, great, I'm done. This is what I will use for my calculator app, and there's no reason to try a different approach. You might conclude. Let's go through the other exercises, though, to see how it fares for some of these other things we want to do. So let's add a new node type, the power node. Same data operation, data members like base and exponent. And now I add a method, which is calculate. So calculate again, pretty easy. Taking something to the power. It's also isolated. No other code needs to change in my whole program. I just add power as an object, a class and objects, and boom, I'm done. Suddenly the rest of my program can handle it. So for example, if I have this other parse tree here with addition of a power, so again, 2 to the third power plus 4, that's this tree. When it runs, again, Python's doing this for me. The add function is going to call, it's going to say, I need to call calculate on my left node. And Python's like, oh, that left node object is a power object. And so I will call its calculate method. The add method has no idea that power even exists. It was defined later. So there's this decoupling in time and interface that provides, which is really nice. So this is kind of the magic of OOP. You can extend it later, and the old code doesn't need to know that it's been extended. It just can keep working, which is great. Let's add a new subclass now. Again, positive integer. This, again, same benefit as one big function. We already have the functionality in calculate. Positive integer, we can add some validation to the initializer, but we don't actually need to implement calculate again. We can just use the base class, the superclass, in this case, the integer version of it, and that works. So that's not too hard. That's not bad. Now let's add another method. Remember, we added the pretty printing function. So let's do that in OOP. So if we want to do that in OOP, you go to the base class, you say, hey, I need a pretty method. OK. And then you have to implement it. And then this is where things start going sideways. So I have to go find every single class that inherits from node, and I need to add a pretty method to it. Every single one of them needs it. And so the problem with that is now I've got these classes that have multiple different things that they're doing, and the code for pretty printing is everywhere. None of it's together, it's everywhere else. It's near the data, which is good, but none of the pretty printing code is in the same place. So I'm trying to build pretty printing or debug pretty printing. It's actually hard for me to see. So when you look at it at this scale, it doesn't seem so bad. You're like, well, hey, I just added a couple of methods. That's not a big deal. But let's see where it goes. And just wanted to say again, it works. If you want to add the pretty printer, if you want to exercise the pretty printing function, you can do that. It works just fine. It automatically finds the new methods and traverses the classes, and everything works. But what happens naturally in a system, and I'm sure many of you have hit this, is that you don't just have two methods, calculate and pretty. You have like 20 methods on a data object. And now you're in trouble, because let's say each of these functions is 20 or 30 lines long. And now you've got like a 600-line file or something ridiculous like that. And so it becomes unmaintainable. And maybe you want to split some of the functionality across different files. Well, if you're using OOP for that, what you're going to end up with is you're going to have one file per class. And in some languages like Java, that's like what you're supposed to do. That's fine. But the problem is that what you really want a lot of the time when you're implementing a system is you want all the related functionality of that system to be near each other. Like, hey, here's calculations and how they work. And here's pretty printing. And here's the solver part of my system. And here's the derivative part of my calculator. Like, you don't want, the classes are more like data members. They're not, the functions inside the classes are not similar to each other. They just happen to touch that data. And so what this really is that the organization of the class is on the wrong axis. If you think about, like, if you're debugging a stack trace of pretty printing, you're going to want to go through all the different pretty printing methods. It'd be great if those were all in just one file, like pretty.py. But with OOP, pretty as a method is in all of the files. So if you want to debug a stack trace, you have to open all of the files just to like figure out which one each one is doing. So just really simple stuff like that ends up breaking down because of OOP. The other thing you get is you get this dependency, maximal dependency graph where each class of operations has all the functionality in it, which means that module relies on everything. So when you're trying to write tests or isolated tests or try to refactor parts of the system, you can't, because the add operation, it needs the numerical methods, it needs the formatting methods, it needs some symbolic math methods. And so you're just stuck where everything depends on everything on the left. But what you really want is something on the right where, like, hey, calculate needs this numerical library. It doesn't need a symbolic math library because that's not what it's doing. So how do we pull apart these dependencies? So that's the kind of where OOP is good, but also where it starts to fall apart. So let's just go over the pros and cons again. It's nice in OOP that the behavior is next to the data. Not too hard to add new methods, and you do avoid a bunch of the duplication that we saw with the isinstance checks with the one big function. You get rid of those. That's good. But that scattering of behavior across these files and classes, that becomes really hard to maintain, and the dependencies also becomes kind of a dependency hell. And also the dispatching is kind of magical. Like, you're like, oh, why did it call that class? It just kind of magically happens under the covers. That might be good or bad, but it's not really visible. Okay, so is there something better that we can do? Actually, I'm going to pause for 1 minute. Are there any questions so far? Does anyone have any questions about this? Is it making sense to anybody at all? Okay, you following me? Okay, great. Happy to hear it. All right, so I want to talk about dynamic dispatch. Okay, and this is a concept. It's actually a very old concept that was first introduced in like Lisp. Many of you might have heard of it. It's called a multi-method. Is one way to think about it. Turns out that Python has this built in the standard library. So I think it's a lesser known class. So the function is called single dispatch. It's inside of functools. It's been there for a very long time. How many people in the audience have ever used single dispatch? Have you actually used it in your code? Oh, this is great, amazing. And then who has never heard of single dispatch before this moment? Yeah, cool. Okay, awesome. So it's there. So let's talk about what it is, how it works, and how do you apply it. So what you do is you declare a function like myPrint. This is not having to do with calculators at all. It's a completely separate example. Just bear with me. So we have a myPrint function here. The default implementation is like, I don't know what that is. It just prints that out. Then you use the myPrint function gets this extra attribute, which is register, which is itself a decorator. And now you can decorate another function and say, hey, if the first argument is this type, then this is the one I want you to call. So I can register an int version and a float version, and I can get different behavior. So if someone calls myPrint, what myPrint's going to do is going to say, it's going to look at the first argument, it's going to look at the type of that, and then it's going to decide which actual implementation, which specialized implementation to call instead. So it's not very magical. It's what it does. It's only on the first argument. You can pass many other arguments if you want to. It just passes those through. But that's the gist of it. One other thing, let me show you that working. So here you go. I call myPrint on 10, 1.23, and hello. So the first one outputs integer 10, right? Because it went to the right function, specialization function. The 123, it goes to the float version that prints out right, and for a string, it's like I don't know what that is. So that's working as expected. One thing that's also cool about this is you don't technically have to name these other functions. You can just put an underscore there, like just leave it unnamed because it's behind the other one. But sometimes it's good to name it because then you can test it independently, which is pretty cool. And we'll get to that in a second of why that's useful. Okay, so it's not that super magical. So now let's apply single dispatch to this problem. So I'm going to have a calculate method or function, and the default implementation is not implemented. And then I'm going to register a function to handle each of the types that I have in my calculator program. So for the integer type, I just grab the node value and return it. For addition, I call the same calculate function recursively with the left side and the right side, add them together, multiplies the same pattern. But what's cool here is that calculate now is smart and knows how to dispatch to the right version, like the specialized version of itself, based on the argument. So the add function doesn't need to know what the type of that is. It'll do it automatically, just like it did with object-oriented programming classes. The method, when you called the method, it went to the right specialization, the right class to actually run the implementation. So let's see what that looks like in practice. So again, I have a parse tree on the left, parsing the formula. This is what the tree object looks like. These are just plain old Python objects. No mystery here. If I call calculate, I get out 20, which is good. So 2 plus 3 is 5 times 4 is 20, I think so. Yeah. And then what's happening is, under the covers, calculate is dispatching. So when you call calculate with a tree, it looks at the object and it's like, oh, that's a multiply. Okay. I'm going to call my multiply with a tree. And then my multiply is going to call calculate on the left. And then it's going to look at the node and it's going to be like, okay, the left side, okay, that's an add. Okay, I'm going to call my add. And then my add calls calculate on its left side. And it's like, that's an integer. And then that, it's just the value, it returns it. Same thing for the, this is a typo. I think that's supposed to be right. Sorry about that. And then same thing down here, where every time you call calculate, it figures out what's the specialized version and it calls it. And it's actually in the call stack. So if you get a stack trace anywhere in here, you'll see the dispatching happening. So there's no magic at all. It's completely explicit, very obvious to see what's happening, why it's happening. Yeah, so that works. Now let's run it through the same tests that we did with the other two, with oop and the one big function. So let's add a power class. To do that, all I do is I register the power function specialization with the math. It calls calculate again blindly, recursively. It says, hey, I need to calculate this thing. I don't know what type it is. Please figure it out for me. And that just magically works, which is great. And if you look at this one, yeah, and so then it's the same thing here, where if you call calculate on the tree, it's going to, sorry, that should have said my add, another typo, my bad. When you call calculate on the tree, it sees that it's an add object, so it calls the add one, and then add will call calculate on the left, and then that calculate will realize that it's a power object, and that'll call your new power function that you just defined. And so it has all that nice goodness, that kind of registration, late registration. You can add whatever you want. It's very extensible. Adding a new node subclass, same thing, just works like all the others. So there's no downside there. Now we start getting into really interesting things. Let's add a new function for pretty printing. This is where object-oriented programming started to fall apart, right? So to do that, I create my function, and I implement that function for all the types that are in the system that I care about, and I'm done. And that's it. And so if you remember that kind of ideal state that we were looking at back here, I can just do that. I can have a pretty.py file that just does pretty printing and nothing else. I can have my object definitions, the classes, just dumb definitions of those classes in another module that's common that has no dependencies. And I can decouple all of my dependencies from each other by doing this. So going back over here, so the pretty printer, it just, each one, this one turns the value into a string, this one turns it into a this plus that, and all the rest. And so you can see I'm using it here. I parse this formula, get this tree, run it through pretty, and then I get like a normalized version of it turned into a string. And it can be totally isolated as in its own kind of package or module without any coupling with anything else or any other functionality. So it kind of seems like the best of both worlds, or dream state. Great. So dynamic dispatch, that's another name for this, because you're choosing where to go dynamically. Simple data objects are still there. I can put the behavior next to the behavior, so all the pretty printing is like near each other. I can isolate my dependencies, so I'm not in that kind of wrong axis organization of the code that you might have seen before. So the code is organized on the right, on the correct axis. The data and behavior are separate, so that is one of the things OOP does have, is that the behavior is right next to the data. Sometimes that's actually better, it depends on what you're doing. It's not as encapsulated, it's just a bunch of functions sitting there that are not necessarily easily associated with each other. Adding a new class, there's a little bit of friction, because when you add the class, you have to go and define every single function for that new class. You have to go to all those places. So let me explain that real quick. So let's say I added a new class. So I have a pretty printing function, and I have a calculate function, and they're in different modules. And now I add a new class like square root. Now I got to go into the pretty module, and I got to go into the calculate module and add register handlers there. So that is a little bit of a higher burden, right? You have to go into multiple, when you add a new data class to the system, you have to go into multiple modules in order to support it. But I would argue that that's fine, because that's the right time to be doing it. When you're building the class, like the code out and adding functionality, it's okay to go into multiple files to make sure you have coverage. What's annoying is when you're debugging a stack and you have to jump around everywhere. So it's like let's optimize for like kind of the bad situations, like debugging and performance and all that stuff, by keeping things in modules, and pay a little bit more of a cost during development time where you're going to be jumping around a little bit more. And in my opinion, that's the better trade-off if you can do it. Okay. Any questions at this point about what's going on, or any confusion at all? Yeah.
But how do you know which files you have to check when you do a new class?
How do you know what? So the question was, how do you know what files to check when you add a new class? And the answer to that is it's Python, first of all. So you're going to have there's no types to save you. What will happen is that if you didn't register the type and it hits it, you'll get a not implemented error raised, because that's the default implementation. So if it doesn't know, so if you have any kind of test coverage or you actually use it in the wild, it won't silently fail, which is part of the Zen of Python. No error should go silent unless explicitly silenced or whatever. So an error will be raised. It's probably going to be at runtime if you have no test coverage, but at least it'll happen. It won't just swallow. There won't be some other weird behavior. But also, depending on what you're doing, if you have a default implementation, it'll just call that. And so depending on your use case, maybe sometimes that's actually just fine, because the default is, maybe it's a serialization library, and that's actually the default serialization is fine. You're just trying to allow for customization. So it's going to be use case specific, but the answer I would say is there will be a runtime error that's expected that you have control over, and you decide what that behavior is. So that's a good question. Any other? Yeah, back there in the red. So yeah, so the question was, if you use type annotations, will it tell you in that case? I don't believe so, but there have been some improvements in the single dispatch library for type annotations. There's an alternative syntax now where you actually can just use the type annotation on the first argument, and it'll look at that for the dispatching. And it would be really cool if it also did some kind of analysis, with some of these type checking tools. I actually am not aware if there is any rule for that in the type checkers, but that would be super cool if there was an exhaustiveness checking built into that, but I'm not aware of that. So, all right, cool. Let's keep going. So, all right, so now I want to talk about this word, which is catamorphism. And if you're freaking out, don't worry, because I do too. I think if anyone's like a functional Haskell programmer in the room, don't tell anybody. But if you are, you're probably like, this is great. I've been waiting my whole life for this, for catamorphisms. So a catamorphism is just the visitor pattern for a recursive data structure. That's it. Okay, it sounds really fancy, but it's not. I'm going to show you what it is, and by the end of this next 5 minutes, you will understand what a catamorphism is, I hope. And you're like, oh, that's not so bad. The word is really bad, but otherwise, but the thing is, we don't bat an eye with polymorphism, right? But somehow catamorphism is like somehow worse. I don't know what's up with that, but personally, I'm very, anyway, we'll get into this. So, all right, so let's talk about a problem with the single dispatch version of this. There's a lot of duplication. You may not have seen it on the first glance, but let's look at it. It's right there, which is like in the add function for calculate and the pretty function for the add module. So calculate dealing with the add node, and the pretty function dealing with the add node. Side by side, look how much of the code is duplicated. All the recursion is duplicated. All the traversal of the nodes is duplicated. So if you think about, I'm going to add a pretty module. Now I'm going to add the symbolic math module. Each of those little functions for dealing with the data types has to duplicate all of the code of how to actually handle the data type. And that's where bugs come in. You're like, I did this wrong. I copy and pasted this from the other one, and I forgot to change the plus to a star or whatever. It's like really, when it starts being something that people want to copy and paste, that's when they're going to copy and paste it, and you're going to get bugs. And it's harder to read. It's harder to maintain. So the question is it possible to deduplicate this logic? And the answer is yes. A catamorphism is a solution. This is what it looks like. And when I looked at this the first time, I thought, okay, the word algebra came in here. It's like, so I need to do catamorphism with an algebra. And I'm like, that's like a monoid in the category of endofunctors kind of statement to me. I'm like, I can't understand that. Like, it's a monad. That blows my mind. So I'm going to take this word algebra, which is really scary to me, okay? And then I'm going to perform a magic trick right now. So is anyone feeling a little nervous about the word algebra showing up here? Because I'm nervous. No, okay, you guys are okay. You're all very comfortable. Well, I think it's very scary. So let's just call it func. It's just a callback function. We all just chill out here. It's going to be an algebra, but it doesn't really matter if that's an algebra. It's just a function. It's a callback function, okay? So that's what you do. So this is a visitor pattern for a tree structure. It takes a node, and it takes a callback function, okay? That's all it does. By default, it doesn't know how to traverse the object, okay? This is, again, using single dispatch. And then you can specialize it. So if it's just an integer class, you say, hey, just call the func with the value that I found for that integer. And for add and multiply, those are both binary operations. So I'm going to go traverse down the left side, and I'm going to go traverse down the right side, and then I'm going to call the function on the results of both of those. Okay? So that's it. It's just doing the traversal in a generic way, and then calling a callback function with the results of those traversals. So left value is one traversal, right value is another traversal, and then it calls the function with the result of both. That's it. Okay? We apply it to an actual, this is the same structure from earlier. Let's apply it there. So we go through the tree for the blue one. It gets called the tree in func. It's going to say, hey, call traverse on the left node, the purple one, with the function. And then it's going to take the results of those two things. I'm just using like x and y here just to show you that I don't know what the function does. I don't know what it's going to return. So something. So it's going to take the result of those two things, and then it's going to call the function again with the node and x and y, the results it got. And that's going to make z. And then it's going to go down the right side, do the same thing. It's going to end up with k. And then it's going to call the function like again with those results. And so really what this is going to end up with is going to call my function 3 times, once at the tree level, and then once at the left side, and once on the right side, with the results of the function being called. Not that complicated. So what is an algebra here? What is the actual algebra? What is the func implementation? Well, it's another dynamic dispatching function that does arithmetic. And so here's my calculator program. If you're a value, you just return the value. That's really easy. If you're doing addition, you just do addition. And if you're doing multiplication, you just do multiplication. All of the calculate recursive calls are gone. There's no recursion anymore. All of the node traversal, node.left, node.right, that's also gone. So I've refactored this. I've factored the recursion out of this code, and I've factored the traversal of the data structure out of this code. I just have these dumb functions. And if I want to write a test for this rth add function, I just call it with 2 numbers and I'm done, because it doesn't even use the first argument. So you don't even have to build a graph of the data structures in order to test it, because you've decoupled structure and recursion from the actual calculation. And that's what a catamorphism is trying to do. So now we're going to go through one of those stack traces again, just to hit you over the head with this explicitly. So I'm going to traverse this. Traverse is using single dispatch. It's going to look at the first the type of the first argument, and it's like, oh, that's tree is an add. That's a binary op that I registered. If you remember, binary op right here. I registered add with that. So cool, I'm going to call that, and then it's going to go do that recursively, and then at the very end, like when it hits a leaf node, it's like, oh, hey, I'm at a leaf node. Now I'm going to call the arith callback function that you gave me with the node value. That's, again, a single dispatch function. It's going to look in its lookup table. It's like, oh, node, that's an integer. Cool, I know how to do that. I'm going to call arith value, and arith value just says, hey, I'm 2. And then it adds them together. It does the left side, it does the right side, and then right here's the magic where it calls my arithmetic again with the add node, and 2 and 3 that it calculated underneath that, and then it calls arith add with 2, 3, which just adds them together as 5. That's it. So again, no magic, but it's pulled them apart, pulled apart the structure and the recursion. If I want to add a new type to this, as we talked about in the other cases, a little bit more work. If I have different arguments here, like base and exponent, I have to create a traversal function, and I have to create a power function. But this power function, again, is super simple. And this traversal function, that could be used for, maybe I would redo the power class to be just like a binary operation class, more generic, and then I wouldn't have to write this. There's kind of other ways to deal with it. But a little bit of a cost here. You have to add traversal functions sometimes. Just like before, it'll discover the fact that it needs to call this traverse power function when it's happening. I've taken the single dispatch parts out of this so you don't see them anymore, just to make it easier to read the stack trace. So add knows it needs to call power, and then when you call the arith function, it knows it needs to call the power version of that. So it all just bolts in just like the other example. So it all just works automatically. Subclasses work just like every other one. There's no downside there. And now we get into the awesome part of this, which is if you want to add pretty printing, this is it. There's nothing else. So there's no recursive call. There's no recursion at all. You don't see any recursion. There's no node access .left and .right. It's just the stupidest pretty printing functions you can imagine to do this, which is awesome. Way easier to test, less surface area. And it works so well, it's like, well, let's add some other algebras. Like, why not? Like, this is so easy. Let's do some more. Oh, and it can be in its own file, like we talked about in terms of structure. And often when you have recursive data structures or big trees, you want to do a lot of different things with them. So one thing that we could do here is we could say, hey, what's the complexity of this operation? So I could say, hey, for every type of operation, maybe this is running on a virtual machine or some kind of hardware, and I want to calculate how complicated this formula is. I can just add a new algebra that calculates the complexity. So I can say, hey, if it's just a value that's there's no complexity, additions are 1 operation cost plus whatever their children are. Multiplies are 2, because whatever the hardware I'm running on, and then maybe power is like a 4, okay? So now I have a way to take the same graph and do a whole different set of operations on it, and look how simple that was. You don't even know it's a graph. You can't even see that here, but it just happens. I just have to pass the complexity function into this traversal. So pretty cool. And you could add more. You could add a type checker. You want to do type checking. Hey, is this going to come out as a rational number or an irrational number? Like you could add type checking, and that's like under the covers. This is what compilers are doing when they traverse trees and stuff like that. This is like they're doing a lot of tree operations like this in a bunch of different ways. And so anytime you have a tree, you kind of want to do a lot to it. And so this is a great pattern. Summary here, it's basically all the same stuff that we had before with the single dispatch, but we've deduplicated all of the structure, traversal, and recursion, which is pretty awesome. It's all gone. Terminology is the bad part. Catamorphism, you have to say that word, but again, you can say polymorphism. You could also call it like the visitor pattern for trees. You know, it's not that scary, and you don't have to use the word algebra if you don't want to. Okay, so hopefully that made sense. We're gonna get questions in just one sec. I was gonna do a bonus thing here, which is I think that a lot of the time in a code base, you actually already have some kind of dispatching code and dispatching functionality, and you don't want to use the standard library. And so we're going to just write our own single dispatch real quick, just so you know how to do it yourself. So there's, again, no magic here. So if you were going to do this yourself, what you would do, and just bear with me, this is a lot of code, but it's not that bad. You're going to create two functions. One's the register function, like, hey, I'm gonna register this type should call this specialization. And you just have a map of like what class calls what function. Okay, really simple. And then when you want to call the right version, you go through this attribute of a class called MRO, method resolution order. It's on every class. It's built into Python. It's always there, and it tells you what order should you consider the classes. So when you call a method, MRO is what it's using to figure it out. So it'll call the functions in exactly the same order as if you have some kind of object-oriented programming system. That's where it goes. So you just iterate through that list, and it starts with the most specialized class first. So you go through that list and you say, hey, in the map, do you have one of these? You know, this really specialized one. Nope, okay, now let's try the superclass. Now let's try the other superclass. And it even works for multiple inheritance. So that automatically is taken care of here too. So that's it. This is all that single dispatch is doing. There's a lot of other stuff that it adds, but that's all it is. So if you're like, hey, I want a dynamic dispatching function in my library or my core, middleware or whatever the thing is, like just add it. It's not that hard. Just look at MRO. That's all you have to do. And this is just boilerplate to hook it up, like with some decorators. And if you remember the example when we started this with single dispatch, that I showed you how single dispatch works, and again, I just replaced that with my own version, and it works the same. So that's it. There's no magic. So to conclude, one big function's fine to start. That's what you should start with. Please don't go straight to catamorphism. That's not a good way to do it. OOP is actually really good when you want cohesion. So if you want that cohesion that we said was bad, which sometimes like UX frameworks and stuff like that, that's actually great. So it's good if that's what you need. Dynamic dispatch is good when there's a lot of data types that are shared, but the systems are totally different. And when we talk about code being organized on the wrong axis, and you can mix the two. You can mix OOP and single dispatch, dynamic dispatch. You can have some common functions and methods on classes that are useful for everything. That's where they live as OOP. And then you use single dispatch for like the larger modules that are kind of have nothing to do with each other. And then catamorphisms, those are good when you have a lot of different behaviors for the same data structures that are recursive that you want to implement. That's a great way to go if you can. Seems like the best of all the trade-offs. And you could have OOP and catamorphisms working together. Cool. This is my book. It just came out late last year. This is the link for the slides that it's in there. All the slides and speaker notes. And there's code that you can run yourself. And there's a discount if you want to buy the book, but no worries if you don't. It's all on that GitHub, and that's the link to it. And yeah, and I can take some questions. So thanks, everybody. Yep.
If you have that person. Hello.
Line up at the microphone. Oh.
Yeah, hello. If you have any questions, please line up at one of the microphones. We have about 7 minutes, and then we'll have to end it.
Hey.
So can you hear me?
Yeah.
So quick question. So as you talk about dynamic dispatch, so we have single dispatch, but Python doesn't have multiple dispatch. So do you know why is that, and do you think it could be useful sometimes?
Yeah, it's just complicated to implement because you get into these corner cases where there's ambiguity. There's actually a blog post that Guido wrote like 20 years ago that actually has an implementation of multiple dispatch in Python, and I believe it still works. And like if you look at Lisp and the Lisp object model, they support every type of multi-parameter dispatch that exists. So there's definitely like state of the art. I think it can be too complicated, and the issue is ambiguity, because you're like, oh, do I prioritize this one over that one? How do you break ties? And so this version is it's the MRO is how you break ties, and so it's very there's no surprises. But you can do that if you find there are use cases where that is really powerful.
Okay, thank you.
Thanks. In the back, yeah.
Have you compared performance across these different approaches?
Yeah, so I think that OOP is going to be a little bit faster because you have that native dispatching happening. There's an extra call frame with the single dispatch version of this, because you're going through a couple extra decorators and a little bit of a dispatching aspect of it. But I think, is like how much performance really is it? It's going to depend on your use case, and is the poor maintenance of your code base worth it? You have to make that trade-off. So there might be situations where you go with OOP for performance reasons, or maybe you shell out to a C module. I would say if this is your performance, if like single dispatch using it in your code base is your performance bottleneck, I'd be shocked, because there's probably other low-hanging fruit. So, but there is an overhead for sure. Calling a function in Python is expensive, unfortunately. So, good question. Up here in front.
Thanks. I've seen some Java programs heavily using OOP in the way that you described. And the issue that we ran into was like trying to debug and really like understand what the crap is going on underneath of all of those multiple layers. And when I look at the single dispatch example, it seems like it would have the same problem where, the stack trace is nice. You kind of get to put everything in one file. But when you're trying to understand like what are all of the different function calls that are going to happen on a single method invocation is kind of difficult. And I'm curious what your experience is with that.
Yeah, I mean, I think that what you could do, if you go to the code and you pick a leaf node and you add a raise, look at the stack trace, because it's actually really easy to read in this case. So single dispatch, it's like, it says it's dispatching, so it's very explicit. And so in my experience, like the fact that it's all together in that file, the fact that you can read the stack trace, the fact that the line numbers are all still in the same file, you can be scrolling the file and the stack trace, lining them up, it ends up being a lot easier than jumping around. So I don't know, maybe that's a subjective thing, but I found that it has the understandability thing, because it's all explicitly done by the code itself. There's no magic, there's nothing being hidden from you, so you know what's being called. So I don't know, I think that's maybe just a subjective preference. So sort of a better answer, yeah. Cool. All right, I think that's it. So thanks everybody, thanks a lot.